Okay. Okay. Sorry for that interruption. So we can continue with this developing the weak form. So this is equal to 0. So looking at this boundary term of the weak form, we can identify that this is the secondary variable of the problem, the coefficient of the weighting function term. And what is that secondary variable? This is the shear force. And what is the primary variable associated with this? Primary variable associated with this would be the transverse displacement. Right? And what is the highest order of derivative? In the weak form, the answer is 1. The highest order derivative in the weak form is 1, and that means first order derivative of the approximation should exist and that means linear interpolation model for the primary variable V should suffice. So it's a primary variable, so linear interpolation model. So we have node I, node j defined as xi, xj. So Ni and Nj, the linear interpolation model is simply given by x minus xj divided by xi minus xj, zeros, Lagrangian interpolation. That's all. And since both for theta we need linear interpolation model, for V we need linear interpolation model, so the interpolation model is same, so both of them can actually can be interpolated in terms of the same shape functions. So identical shape functions, interpolation functions should suffice. So the interpolation model V and theta approximation can be given as Ni 0, 0, Nj let me arrange the variables first. So Vi, theta I, Vj, theta j. So corresponding to this, we have Ni x 0, Njx 0, 0, Nix, right? So V hat is equal to Nivi plus Njvj. There is no representation of theta in this interpolation of V. Similarly, theta interpolated independently in terms of theta I and theta j. So Ni theta I plus Nj theta j. And that is what the interpolation model is. So V hat x as sigma Vi Nix. And theta, similarly we have theta as interpolation model I is equal to 1 to 2 theta I Ni, right? So we can write here instead of Ij we can have 1 and 2 and 1 and 2 here, so whatever. So the governing differential equations, once you substitute this in the weak form, these are the weak form of the statement. So we can substitute that. Once choose W as N1 and N2 and we get the equations for so for first row, by choice of W1 as N1 we will get one equation. For choice of W1 as N2 we will get another equation. Then for the second row, for the choice of W2 as N1 we get one equation. For the choice of W2 as N2 or Nj we get another equation. And together, I mean, once we evaluate these, we will get four equations, equilibrium equations in terms of four unknowns, and that is what we can assemble, and that will be the element equilibrium equations for shear flexible beam. So let's work out that. So let me first arrange, just for purpose of demonstration, I can write this governing differential equation that we had earlier. This equation I can write in terms of the operator form as So that is the governing differential equation in operator form. So this is what we refer to as the operator. So this is the governing differential operator L, and this is the vector of unknowns V and theta of the problem, and Q is the known function, vector of known functions. Right. So that is a standard operator form, and we can develop the weak form. And yes.
I think the first equation is the operator.
First equation is not agreeing. Okay, let us see. What is the first row of equation? Minus kga dv by dx plus d dx ei d theta by dx plus kga theta is equal to 0. So
the second one is multiplied with
pardon?
Multiplied with theta.
So this is theta, kga times theta.
Okay, I understood. It was d by dx. I thought it was regular with d theta by dx. Sorry.
So fine. So we can work on that if we require. So the differential operator form, we have L u plus what? Okay, let me just say L u plus t. Let's just say is equal to 0 in omega. The weighted residual statement is given by omega matrix W multiplied by these matrix equations or the combined coupled equations. That's a null vector. So this is what we have arrived at from this differential weighted residual statement, and we can develop it in okay. We can develop it in the matrix form. So that transpose is just to make it consistent with the conventional notion of dot product. So it is the projection that we are taking. Of course, it doesn't matter because W is a diagonal matrix, so transpose is immaterial. So eventually, what we will have here is these boundary terms that we have. N1, if we choose N1 will evaluate to 0 at the node J, and it will evaluate to unity at node I, right? So this will evaluate to minus ei d theta by dx at xi minus integral, what do you have, dni by dx multiplied by ei d over dx multiplied by n, and what do you have? Theta hat, approximation for theta hat. So n1 theta 1 plus n2 theta 2. That is the first term, and minus, and this is between xi to xj, the element coordinates, xi to xj, ni multiplied by k times ga ddx of n1 v1 or ni vi plus nj vj. Right, so okay, ni theta I, nj theta j, and this is 1 and minus, of course there is ni theta I plus nj theta j. So equal to 0. So that is the first equation that you will have. Right. So let us arrange terms. Ni so you have this equation. Where did it go? Minus ei d theta by dx evaluated at xi minus dni by dx and what is this ei times d theta by dx. Ni theta I plus nj theta j dx plus, or rather minus, ni to 0. So that is the 0 is equal to this. So that is the first equation, and by choosing W is equal to Nj, we will have another equation by substituting this Ni with Nj, W weighting function, and these two will provide us two equations in terms of these variables. Vi theta I and Vj theta j. And similarly, when you choose the second equation and again choice of W2 as Ni and choice of W2 as Nj, you get another set of two equations, and together we have four equations. So I expect all of you to please work it out and get these four equilibrium equations ready for assembly when we resume our lecture tomorrow morning. Thank you. So any questions?